like I said, we're going to do a little bit of review from yesterday here, and I'll record this here part. But lesson 8, just remember covalent bond, of course, we're sharing electrons between two atoms, two or more atoms. They're covalently bonded together, and we use Lewis structures, of course, to represent that. Yesterday, I kind of screwed up on the order we did this, but we'll kind of go through that today a little bit. I feel bad for you. I apologize. This is the rules for drawing simple molecules or polyatomic ions. I don't know if we always need to use the rules, but I'll show you kind of both ways to do this, and then you can kind of decide what's going to work best for you. There is a couple things to keep in mind, though. It does get a little complicated at times, but for the most part, it's pretty straightforward. It looks like there's a lot of rules, but it's actually not that bad. So this one here, basically, to summarize this first point here, just basically says we need to add up all the valence electrons. And of course, if we have Lewis diagrams, we know how many valence electrons we have, right? So lithium would have 1, and oxygen would have 6, and fluorine would have 7. So that's kind of what we're going to focus on in the first part. It does say if there's charges, we need to add or subtract electrons. So we'll get to that later today, polyatomic ions. So like if I was drawing sulfate, SO4 2-, that means that's implied as gain 2 electrons, right? So we have to add those electrons into that compound kind of thing. So we'll talk about that when we get to that part. Okay, don't worry about it yet. This is always true, though. We're going to always choose the atom with the most bonding capacity. We talked about that yesterday, yes. The most unpaired electrons, basically. That's the one that has to go in the middle, the central atom. We draw what we call a skeleton structure around it, so we kind of put the other atoms around it. And we decide, okay, this is going to be my central one. Here's the other atoms. Usually there's 4 positions around the atoms for the most part, because of course we go, 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, right? And then we start to double them up, right? Kind of like that, right? So, so there's kind of 4 positions around the central atom usually. Sometimes they're filled up with bonds, and sometimes they're filled up with what we call lone pairs. Okay, which are pairs of electrons that are not involved in the bonds. We draw on a pair of electrons between the center atom and the outside atoms. Okay, that's how we connect it together. That's how we make that bond. Then there's a whole list of this stuff here, and it's like, if you've done the outside atoms, place lone pairs around all the atoms except the central atom to form octets. Hydrogen, remember, only can have 2. If all the outside atoms are filled up and have their octet, we can put some on the center one. If we run out of electrons, we might have to move some pairs of electrons, right? Again, we'll get to that, okay? I think it's best with examples. Yeah, there's all the notes that we took yesterday. So yesterday, I'm just gonna do a quick little review here. We had carbon tetrahydride, and remember, always start with the formula, right? Whether if it's given to you, fine. If it's not, if it's carbon tetrahydride, write down the formula. Start with neutral pairs of atoms, C, H, 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 and H, okay? And maybe down the road, maybe we don't have to go through this extent, but we're kind of just learning here, so we're going to take this kind of slow. We're going to look at bonding capacity, or basically unpaired electrons is another word to say that. So BC is going to stand for bonding capacity. What's the bonding capacity of carbon again? 4, okay? What's each hydrogen here? How many bonds can it form? 1, okay? So that would help us basically add up the electrons as well if we were going to follow the rules, yes? Okay, and I'll do that actually as well today. So maybe should I do that first maybe? I don't know. I don't think it matters. Yeah, I don't think it matters. Regardless, whichever way you want to do this, we're going to put C in the middle, yes? Because it's got a bonding capacity of 4. So we want to put C in the middle, central atom. Central atom. And then basically in this case here, it's pretty straightforward for the most part. The H's kind of match up, like there's 4 unpaired electrons, and we have 4 hydrogens that each can form 1 bond basically, right? So I don't think it's too much of a stretch to say, okay, well, we're going to put 1 there, 1 there, 1 there, and 1 there, yes? Okay, and then of course we'd probably show a line between them. We don't have to show lines, by the way. Sometimes you'll see this, so you'll just see this. Sometimes it's written like this. Okay, also acceptable. Sometimes you'll see they use a dot and then an X or something to represent this electron comes from the carbon, this one came from the hydrogen, just so you know. So like be like, okay, there's an X there and an X there and an X there and an X there, for example, just kind of showing you, hey, the X's came from the hydrogens or something, and the carbon had those 4 dots there, kind of thing. It doesn't matter. Or probably the best thing here is, of course, we have this from yesterday, which is single lines, of course, which represent 2 electrons that are being shared. Okay. And then yesterday we talked about, well, how does this happen? Well, hydrogen each has 2, of course, 2, 2, 2, 2, right? And then the carbon has its octet, which is, of course, 8. Okay, so 8 there. Okay, and we're sharing, right? And we'll talk about why, how do we know if they're sharing or giving and taking? We'll get to that part eventually here. Okay, but that's kind of what we're going to look at today. Yes, good. Questions? If you're going to use the rules, okay, I'll just start on this page here. Carbon had, like I said, this. Okay, this has got 4. We add up the electrons, which is 8. Okay, so this might come in handy as well, and you might want to do this for all the compounds that you decide. It's up to you. I would say for polyatomic ions like sulfate, SO42- and nitrate and carbonate and things like that, I would definitely use this because we have to account for extra electrons, and it's probably the only way that it's going to work out probably. For simple molecules, I probably wouldn't go through every step exactly, although we're kind of doing that anyway, okay? So I got 8 electrons. I'd pick C as the central atom, and I'd draw a skeleton structure around basically C. So I basically put atoms around there, okay, whatever that is. If there's 2, if there's 4, perfect. If there was 3, I'd put 3 in there, you know, and I just kind of pick where I want them to go. If there's 2, I'd probably put them on either side of the hydrogen. If there's 1, well, we don't have a central atom, so that's a different issue. Excuse me. We have 8 electrons. It says we need to put a pair of electrons between the outside atoms and the central atom to make a bond. So I'd say, okay, I'm going to put 2 electrons there to make a bond between the outside and the inside. That's how we get a molecule, right? That's how we get a compound. We have to connect the C to the H. There, there, and there. That's 8 electrons. We used them all up. We make sure the outside atoms are happy first. Does hydrogen have 2? Yes. Hydrogen, yes. And then we make sure the inside atom also has 8, and it does. So we're done. Okay, and that's all we do with that one. There's nothing else to do. So we kind of ignore the last little bit of that of the notes there from yesterday. Okay, water was the next one, I think. Is that correct? Okay, so water again. Okay, I'd say, okay, well, first of all, let's make sure we have let's have a list of atoms, neutral atoms, maybe to start with. Hydrogen has 1. Hydrogen has 1. What's the bonding capacity of oxygen? 2. Okay. Now, here's where we have to be a little bit careful. Okay, because bonding capacity and counting up electrons is different. Yes. Okay. If I was going to pick a central atom, this is what this tells me. If I was going to pick a central atom, I'd go with oxygen, right? So I'd put my oxygen here probably. Looks like that. Okay, 1, 2, 3, 4, 5, 6. Double them up. Yes. And then where would I put the hydrogens? Well, I'd probably put one here. Hydrogen. Hydrogen. Yes. And then right away I'm saying, well, those 2 could share, right? That's why they pair up to share. So now I'd get something that probably looks like this. Good. And that's what water would look like. And in fact, that is what water looks like. It's what's called a bent molecule. Okay, that's why it's polar, etc. We'll talk about that. Good. This is where I don't like the adding up of electron thing, because this is, it's not that it's wrong. It's just that we have to be super careful on how we're going to interpret that drawing, because that's going to be a part of Chem 20 here, coming up in like less than 10, 11. So if I'm going to add up electrons, remember, if I'm going to have H2O, well, I have 2 here and 6 here, yes? I'm adding up all the valence electrons, right? That's how it's a little different between the 2 of these, and that's 8 electrons. This basically, this part here just tells you which one's going to be my central atom. Okay, that's all that's doing. This here is saying, hey, here's all the valence electrons that need to be shared or that are present in this structure. All right. So there's 8 electrons. Again, I would put O, and I would draw what we call a skeleton. O is the central atom. I would draw count up the electrons. O is the central atom. Draw a skeleton structure. So if I was going to do this, I'd probably put an H here and an H here, just because I want to keep it kind of symmetrical if possible, ish, kind of. Not always, but usually. Okay. And then I'm going to start putting electrons to connect the outside atoms to the center atom. So I'm going to say 2 is going to go here. That makes that bond right there. Yes? Are we clear on that? We got to connect the outside atoms to the center, otherwise we don't have this molecule. Yes? And I put another 2 here. That's 4 so far that I've used. Yes? Now, the notes say you got to make sure the outside guys are happy first. So anything on the outside, they have to have their octet. So the question is, does hydrogen have its 2? Yes. Does hydrogen have its 2? Yes. Now I can go to the central atom and put on some what we call lone pairs to fill up the rest of the oxygen, or to fill up the rest of the octet, if I have room for that kind of thing. All right. So there's 4. I could go 5, 6. That's called a lone pair, by the way. Make sure you know that. Okay. 5, 6. And again, does oxygen have 8? No. 7, 8. There's my total 8 electrons that I can use. Okay. So, do you see the difference between the 2 drawings? They don't really look the same, do they? I don't think they do. This here would tend to make me believe that this water right here, this bottom one, if you're at home, this one here would be more of a linear molecule, yes, kind of thing. And water is not linear. Okay, it's bent. Now, can you do this and still get the right answer? The answer is yes. However, you have to be, like, that's probably a more representative, that's not a word. That's probably a better drawing, I guess, is what I'm trying to say, than that is. Okay. Could you still get the right answer? Will I still mark this right? Yes, I will. Okay. Sure. But the next part will be the general formula, we call it, and we have to make sure we interpret that right. Because if we don't, then the other 5 columns are wrong. Okay. And that, as we say, that ain't good. Okay. So we have to make sure we interpret this diagram right. The better diagram is usually this one here. That's why when I said, hey, let's draw some oxygen, that's why I said, hey, let's start here, 1, 2, 3, 4, 5, 6, because that kind of is the way that it forms, right? It forms this bent molecule, okay? What's the next one? So that's probably, oh, yeah, we did both ways, yep. So let's see, what's our next one here? Oh, CO2, we're gonna jump right to there, okay? Sounds good. Okay, let's do some CO2 then. Let's see, CO2. Well, first of all, of course, we'd have, let's write this down, carbon dioxide. And then, of course, again, anything I give you, you're going to write out the formula. Yes, CO2, carbon dioxide. Now, I guess, I'll do both ways for you. But carbon looks a little something like this. Draw out some neutral atoms. Carbon, oxygen, and oxygen. Okay, so there's a 2 there. Which one? Sorry, I'll let you catch up here. No one brought coffee today, I see, eh? Oh, interesting. Which one go? Which one is the central atom? Which one do I want to put in the middle? Carbon. Hey, guess what? Carbon's really good at being in the middle, yes? Because you're not going to find anything that's better than carbon, right? Except for the only other one would be silicone, yes? Why is that? Look where they are. Carbon, silicone. Hey, look, 4 valence electrons, yes? So if you got a carbon atom, you probably should stick it in the middle, yeah? Because it's got 4 unpaired electrons. So we'll stick that one in the middle, like so, okay? And again, we want to kind of spread stuff out. We want to keep it symmetrical if we can. That's not the be all end all, but you know, I'd probably put an O over here You might say, well, can I put it on the top, Mr. Bachek? You go right ahead, but then I'd probably put the other one on the bottom, yes? Just kind of spread them out a little bit, okay? So I'd probably do something like that. And if I'm gonna, look, if this is the central atom, if C is the middle, the central, and I put one here, I gotta put the other one over here, yes? And what I'm gonna do is I'm gonna do a little flip-flop here. I'm gonna basically just flip it over, okay? In the big scheme of things, remember, we're drawing this, but this is not really what's happening because these electrons are moving, yes? So it doesn't, all I did was the mirror image of it. I just kind of flipped it over just so that they kind of match up a little bit better, that's all, okay? But, you know, these electrons are moving, so this is, I mean, we're trying to draw something, first of all, two-dimensionally, which is really three-dimensionally, and secondly, we're trying to say, hey, these are where the electrons are, so they kind of match up, and then realistically, they're just zooming around and around, so, you know, it is what it is, right? So the first thing I'd say is, well, you know, when these three get close enough together, look, these two here could share, so we're going to connect these two, and these two here could share, okay? Kind of that whole idea of connecting the outside atoms to the center one, yes? That's kind of what this part is. And then, of course, you'd say, okay, well, am I done? And of course, you see some unpaired electrons there, yes? And the next thing would be, of course, well, look, if you have unpaired electrons, if you have an electron by itself, there's no way you could have 8 around that atom because 8's an even number, right? And everything else is paired up in nicely 2s, right? That's evens and odds kind of thing. 2 right here, 1, 2, 3, 4, 5, 6 right here, 5, 6 right here. There's this bond right here, 5, 6. But there's 7 right here, right? So I don't have enough. When we have to make sure the outside guy's happy, we also have to eventually make sure the inside guy's happy too, but we have to make sure that they're happy. So how am I going to get another electron there, or how is that going to work? Well, look, there's an electron that's free right here. Why don't we pair these two up together, okay? So let's connect these two together here. Maybe I shouldn't use arrows, but let's connect those two together and make what we call a double covalent bond between these two atoms, okay? So I'm just going to redraw that here. So we have this so far. Oops, my bad. That's not true. Oh, stop it. Oh, come on. There we go. Okay. So like I said, if we connect these two together, you might say, oh, how do you know it's those two? Because I just picked them. They're on different atoms, yes? Like one was here and one was here, and I said, well, let's just join them together. Well, why not pick the top one? We're going to do that for this one. I don't know. Pick one. Okay. So we get this double bond, and then again, we had this kind of thing before, and I'd say, well, look, this is great now on this side. This looks better because I don't have any unpaired electrons, but that side doesn't look quite right now. And I'd say, well, look, we got an electron right here, electron right here. Let's get rid of those two, and again, let's make a double bond between them. Okay. So we get kind of this thing here, and of course we always want to check. I mean, this is the beauty thing about this is you can always check to see if you did them right, you know, because the whole idea here of why are we doing this? Well, because we need to have 8 electrons around each atom. We need to make sure that there's still an octet. That's why they come together and share. Look, 2, 4, 6, 8. 2, 4, 2, 4, 6, 8. And then again, 2, 4, 6, 8. Okay, so we're good, right? This would actually be a linear diagram. This is actually true. This is linear, okay? And that's would be very different than water, okay? All right? So sometimes we might have to put double bonds there. If you want to add up electrons, I'll show you that real quick here too. Carbon has 4, oxygens have 6 and 6. That's a total of 16? Yeah, 16. I'll get it right here. Need a calculator, which I have right here. 16 electrons, that's the total for this one if you want to add the electrons. So that's step 1. Step 2 was pick the one with the best bonding capacity, put it in the middle, put a skeleton structure around it. So I'd probably put the O there and O there, okay? Make sure you put a pair of electrons between the outside one and the inside one. That's step 3. Now I've got the outside connected to the inside. we have to fill up the outside atoms first. We have to make sure that the outside guys are happy, okay? Outside guys have to be happy. So we're going to go here now and go, we have 16. By the way, I've used 4. 1, 2, 3, 4. Yes, so far I've used 4 electrons. We have 16 to use. I need to make sure the outside atoms, the oxygens, are happy first before I can do anything else. So here I go. 4 altogether. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? Good so far? And I did that because, remember, I kind of don't want to do this, but I'm going to do. There's 8 there. That's what I worry about first. Yes, and I'm getting rid of that for a second. And there's 8 around this bow here, so that's good. Yes. Okay. You want to make sure the outside guys have their 8 electrons. Then, okay, in the notes it says make sure the central atom has 8. Does it have 8? No, we're short. Right? We only got 4. So then it says, okay, well, if the central atom doesn't have enough, we need to move pairs of electrons in, basically get them to be shared. So right now, the problem is these two, like, I'm just going to pick these 2 right here. I don't know why. You can pick any 2. But those 2 only belong to the oxygen, yes? But if I take those 2 and I move them between C and O, then they belong both to C and O now. They still belong to O. So if I take these 2, watch this, take these and put them there. They still belong to O, but they also belong to C now. Yes? And now I have 6 electrons around the central atom. And that's okay, but now I need to do something about something else here. Okay? So I'm like, well, okay, that's good. I got 6. Let's take this pair here maybe and shove them into there, for example. And that would, again, get rid of just belonging to that O, and now they belong to both. Okay? So I take that pair, for example, and I stick it into here. Okay? And now, again, let's see if I can get rid of this stuff here. Oh, it's not going to be easy. Now I have 8 still, okay, because those pairs still belong to that oxygen. But now this carbon also has 8. And of course, this is a double bond here technically, right? 1, 2, yes, sharing of electrons. And that's how I get the double bond, okay? So you could do it that way as well. Questions, anyone? Yes, no? Questions? Don't be shy. All right. Yep. Yeah, I was going to mention that. So we're going to end up with something like this probably. Okay, and just so you know, I mean, I'm not too concerned about it right now, but technically, when we get pairs of electrons together, remember one spins one way and the other one spins the other way. Whatever. And they pair up and they're unique like that. But pairs of electrons don't really get along with each other. So this pair of electrons probably doesn't want too much to do with this pair of electrons. And you're going to say, well, yeah, but they're, like, you know, they're right here. But you got to remember that we're trying to draw this kind of, it's goofy, right? I mean, this is 2-dimensional. It's not really. Electrons are going around and around. They pair up and try to repel each other, kind of. It's something called Vesper, which we're going to talk about in lesson, I don't know, something. This unit, and basically it stands for valence shell electrons pair up and repel each other. So when they pair up, they tend to push each other away, kind of thing, and that's what leads to these diagrams basically. So usually what I'd say is we're going to leave those there because we have to represent a double bond between C and O, and there's not really any other way to do that without getting too far apart. But this pair of electrons would probably go there, is probably what would be probably a good diagram to try and get away from these here. So they're going to go here, and this pair of electrons would probably go about here, kind of thing. So they kind of try to spread themselves out as best as possible from each other. Same thing here. They'd actually kind of probably go there and there, kind of thing. So put them on a bit of an angle. Just kind of like, you know, if we went back to this here, you know, H2O, you'll notice that this pair and this pair, and this pair, and this pair are kind of as far apart as possible as they're going to be, right? These two are bonded together, or these two are bonded together, and then this and this are kind of far away from that, okay? So we'll talk about that coming up, but that's probably same thing, same kind of idea there, okay? N2, we'll do that one real quick here. This is just plain old nitrogen, right? If you're drawing nitrogen, I'm just going to do this the simple way. I'm not going to add up electrons. Well, the light came on. Right? Maybe for some of you that's true. That's weird. That's okay. All right, it's a sign, people. It's telling you this is the way to enlighten yourselves. Pay attention in Chem 20. That was a joke. You can laugh. Feel free. Evan, how was your walk home yesterday? Yeah. All right. When these two atoms get close, why does nitrogen come in twos? Well, because when they get close enough together, right? When they get close enough together, they will share these unpaired electrons. By the way, nitrogen has a bonding capacity of what? 3, yes? 3 unpaired electrons. So it's got a bonding capacity of 3. So does this nitrogen, by the way. And, you know, look, hey, we could kind of share those two. We could probably share these two here. And you might say, well, this one's over here and this one's, yeah, but they're on, you know, they're on the same atom. Look, and they're going around and around. So we could kind of share those two, and you got kind of a happy face there, don't you? Okay. Now that's a really bad diagram. Do not do that, I swear. That bothers me so much. I'll mark that so wrong. I'll take 500 marks off, I swear. Whether I like you or not, Spencer, I don't care, okay? The best obviously don't do that, because I don't know what that is. Okay, that's not chemistry. That's a smiley face, and we're not smiling here, people. We're learning. Okay, those two things don't go together. So we're gonna put a triple bond in there. Okay, that's the 1, 2, and then the smiley face there, 3. And probably the best diagram, because like Macy asked before, where do I put the other electrons? You can put them up here. That's not wrong. Okay, that's okay. But probably the best diagram is, again, we want to get these things away from each other. And when we play with the model kit, which is going to be a little tricky, but I think we should, basically it's like Lego. When we play with that, you're going to see that there's only certain spots that these electrons can go. Okay, it's kind of really, really limited. Okay, good. That's nitrogen. I'm not going to add up electrons for that one. What's the next one here? Oh, CHCl3. Okay. So now this one we don't know. I wouldn't be able to give you a name for this because I don't know what we'd call this. Well, I do actually, but it's Chem 30. So well, that's not our worry. But I just give you this formula and say draw this kind of thing. Well, again, I'd probably start with carbon, hydrogen, Cl has 7, right? Cl has 7. That's why I'm saying you got to be good at Lewis diagrams. Yes, you have to be good at Lewis diagrams because that's going to help you so much, and you have to be quick at them too, because then that's going to help you draw them quicker, and then we can get to the other stuff, because this is step 1 of like 7, basically, eventually. All right. What's the bonding capacity of carbon? 4. What's the bonding capacity of this hydrogen? What's the bonding capacity of chlorine? What? 1. Okay. And again, we have, those are the bonding capacities, yes? Now, if you're adding up electrons, that's different. Okay, we can do that if you want on this one. But I'm going to go with carbon in the middle, of course, yes? And usually, these carbon ones work out pretty well. You know, they kind of just match up nicely. I'm going to put in hydrogen here. I'm going to put a Cl here. And I'm going to put a Cl here. I'm going to put a Cl here. And look, they match up pretty nice, don't they? You know, for the most part, this is what happens. They match up really nicely. Do you have to add up electrons and all the other stuff? That's up to you. I mean, I'm giving you options here. And I'd say, well, let's connect those and connect those and connect those and connect those. If you're going to do this, I caution you, you better not leave an electron kind of like not covered up here. If you leave an electron like that, then I'm not sure what that means, and I'm probably going to mark it wrong, because I love looking for errors, you know, That's what I'm all about. So make sure you don't have just dots hanging out somewhere, because I don't know what that is now, and I assume that you don't know how to draw it. Okay. So that would be carbon, hydrogen, and 3 chlorines. Again, if you want to add up electrons, that's a little different, right? We're going to go what? 4, 1, 7, 7, and 7, right? We have to add up all the valence electrons because you're basically drawing all those valence electrons. So what is that? Let's see. Quick math here is what? 26 it should be? No. Yeah. 21 and 5 is 26. Yeah. 26. I can do this. Okay. And again, you would just draw a skeleton structure, right? Like C has to go in the middle, CLs go around H, you know, that everything has to go around C. So 4 positions. And again, I was going to say something here, I forget now, but man, I don't know. I would start putting in some electrons. So I had what, 26, I think I said? Is that right? So 1, 2 would go there. 3, 4, 5, 6, 7, 8. Okay. You got to connect the outside ones to the center one. That's step 1. 2, then you got to go to the outside guys and make sure they're happy. Is hydrogen happy right now? Yes or no? Yes. Hydrogen's got 2, right? We're done. Is chlorine happy? No. So where am I? 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, okay? I've used up all the electrons, right? All of the outside guys are happy. Is the inside guy happy? Does carbon have 8? Yeah, we're good. That's it, okay? I'm not going to bother drawing, but basically that's another option. Oh, I know what it was. How do you know how to put the H on top? The answer is, who cares? Don't care. Put it on the bottom. Put it on the side. Be a rebel. I don't care. This is your chance to express yourselves, okay? Okay, good. Questions? All right. Now, we're going to do 1 or 2 more here, and then I'm going to be quiet. Geez, this is taking a long time. We did that one. Let's see. Oh, that one. C2H2. We'll do that one real quick. C2H2, dicarbon, dihydride. Okay. Dicarbon, dihydride. And again, okay, carbon has 4. We'd start with, 1, 2, 3, 4, 1, 2, 3, 4. Hydrogen's got 1, hydrogen's got 1, yes? Okay. Now, actually, this is a good thing we're doing this, right? First things first, what's my central atom? Carbon, yes? Which one? Both would probably be a good answer here, yes? So if you got 2 or more carbons, you probably want to put them in the middle because carbons really link to carbons really well. It's called organic chemistry, otherwise known as hydrocarbons, okay? So I'd probably say, yeah, let's put them, look, if you put, well, it doesn't really matter how you do this, but you really don't have any other options because hydrogen can only form 1 bond. No offense to hydrogen, but it's kind of, as far as middle atoms go, it's not great at that because once it bonds once, it's over, right? That's it. So, we're going to put carbons in the middle because at least we can form some bonds here. Where am I going to put the hydrogens? I'd probably try and stick, you could put them here. I wouldn't want to put them, like, obviously these 2 are connected together right now. I'd probably put 1 here and 1 here for just the time being, just to get them kind of on either end of the carbons, right? Could you put 1 there and 1 down here, for example? Could you put 1 down here just to, because you want to express yourself, you want to be different? You can, okay? Absolutely. It's fine, but, okay, it's probably better if we kind of try and keep it symmetrical a bit because that's kind of what happens for the most part. And I know that's a little bit strange to say that because you're like, well, how do you know? The answer is because there's only so many ways that these can combine together. Okay, and that's really the molecular model kit. When you see that, there's only certain ways that they're going to combine together, and there's only going to be so many positions left for the hydrogens to go into. And then, of course, they'd say, well, you got to connect the outside to, you got to connect these 2 together, you got to connect those 2 together. We got to make a molecule. We have to connect them together. Okay, and then you're going to see you got dots left over, and that's never a good thing. So probably unlikely that these two are going to stay separate. They're going to probably share right there. And we'll make another bond there. And again, these two should probably share here. And again, they match up pretty nicely. Hydrogen's got 2, each carbon has 8, and then the hydrogen has 2. Okay, good. All right. Good. Perfect. All right. There was another one here. I don't know if I want to do that. What do we got for time here? Yeah, you know what? I think we're going to take a break because that's some stuff to consider. Then in that case, I think I am going to do this one here. HCOOH is the next one. I'm just going to do this last one here, I promise. Now, this, I'm going to tell you, this is probably not obvious to you or whatever. Obviously a bunch of nonmetals, but when you see, does anybody remember what this is responsible for? The COOH probably? Anybody? Oh, this is probably going to be an acid if you put this into water. So that's kind of tells you that that could be an acid there for sure. Okay. The other thing too is you'll notice that you might say to yourself, why didn't we just call this H2CO2, which of course would be carbonous acid or carbonous acid? Why didn't we call it H2CO2? That'd be easier, wouldn't it? Combine them together. Why did they do that? What do you think? Why did they write it out instead? Come on. Yep. Yeah, probably because of the way they bond together. They're trying to give you a little bit of a clue here that says, hey, this is kind of the order you want to go in here, roughly, give or take a little bit here. We're going to learn that right away here, but this is kind of the way you want to go here. Which atom do you want to start with in the middle? Which one do you think? Yep, always carbon. So carbon's going to go here. Now, there's a chance I'm going to draw this wrong, so you might want to just chill for a second and just watch, okay? So just be patient here. And it says, well, carbon's going to go in the middle. There should be an H attached to that, probably, so I'm going to put that here, so that takes care of those two. And then I need to put an O, probably O next. So I'm going to put an O here. Now, here's the deal, okay? If carbon's going to be in the middle, should I put another O, like, you might say, well, should it, like, there's an empty electron right here, yes? So should I put another O here, kind of thing? Is that an option? It is. Is it a good option? Probably not in this case. So as much as you want to be like, this has got to go in the middle, you can try this, okay? And then, by the way, that would be this O here, and then you'd have an H to add on. And if you put an H here, by the way, kind of thing, and if you did this and this and this and this, this is what happens, yes? And that's obviously not good, right? Because there is absolutely nothing you can do to fix this, is there? Like, you can't connect another, those two electrons are on the same carbon, yes? So what are you going to do with that? You need an electron on this atom and an electron on this atom to share, yeah? But right now we've drawn it with 2 electrons on the same carbon, and that's probably not a recipe for success there. So, you know, and if this happens and you're doing it this way, then I suggest you grab this, right? Pencils and pens have erasers for a reason, and you just kind of say, well, that's not going to work, so obviously something went wrong here. Let's go back to this part here and say, okay, well, I'll put an O here, and instead of putting an O on that O there, maybe I want to put the O on the carbon, for example. I'm just going to get rid of this first. I need a little bit more room. So maybe I want to do something like that, and all I do is kind of turn these atoms a little bit so that the pairs of electrons kind of match up, yes? And for right now, look, H is the easiest one to do, right? Don't forget, I still have to add an H on. I'm going to worry about that a little bit later, okay? I'm just going to worry about this stuff right now because this is going to be my issue. So I'm going to say, okay, we can put a pair there, so that's okay. I can do this too, can't I? Now, look what's left. I have an electron here. I have an electron here, and actually have one here too, yes? So could I make a double bond there? Could I do that? Sure. There's an electron, this one here and that one there could make the double bond, yes? Could I make the double bond between these two, which is probably what most of you kind of saw in the first place? Sure, you can do that too. Sometimes there's a little bit more than one way to draw this, but it doesn't matter because sometimes we call these isomers. In other words, they look the same, they have the same formula, they're just written a little differently. In this case here, it's actually not different at all, okay? But so you might want to connect those two together. Sure, you can do that too. But the ultimate thing here is we do need to connect, you know, a pair together somewhere. Either that one, the top one, and that one, or the side O and the C, regardless. And don't forget, we still have an H to go. So let's put that here, and there you go. Okay, so it might take a little bit of tinkering. Is C in the middle? Kinda, yes. Okay, this gets a little confusing, but yes, it is technically still the central atom. And probably the best diagram of this, just so you know, would look a little something like this here. I'll kind of redraw, it doesn't matter. But Mitchell, you okay there? Yeah. Everybody's got happy, look, 2, 8, there, yes. 2, 4, 6, 8. 2, 4, 6, 8, and 2, yes. So that's how they kind of help each other up become more stable. Now, again, is carbon in the middle? Yes. Usually we put the double O on top here. It doesn't really matter, but that's how we usually represent it. We'd put an H out here, okay? And then we kind of try and get these bonds away from each other. And then we'd have a what? Double bond, and then I'd have the O here. And, well, actually, probably a little bit better diagram would be something like, okay, something like that there, okay? It's fine, but that's kind of a little bit more complex one, okay? All right, questions, anyone? Okay. And again, you could add up electrons for that, but you'd have to make sure that you kind of plan them out a little bit as to where they're gonna go. And in this case here, the skeleton structure, this is like the most complex one. You're probably not gonna get too many like this, maybe one just for fun, but most of them are pretty simple, right? Pretty simple. So let's see here. Let's find your homework. Just a couple things about this homework here. So before you start taking pictures or writing stuff, just listen. We're going to draw these out, okay? And some might be a little bit of repeat, but it just kind of gets you in the practice here. I think that's all good. This here is arsenic, right? That's AS, by the way, arsenic. Now, when you look on your periodic table, you have to remember certain things about the periodic table, right? How many electrons, how many valence electrons does arsenic have? Look at the periodic table, find arsenic. It's, or look on yours and find arsenic, because there's a really bad glare right now. So how many valence electrons does arsenic have? How many? Yeah, 5, right? How do I know that? Because it's the same as nitrogen and phosphorus, isn't it? Nitrogen's got 5, phosphorus has 5. Arsenic will have, we're going to say 5. It acts the same. It's 3 short of having a full outside energy level, yes? That's all we need to know. So arsenic is the same as nitrogen or phosphorus. That doesn't change, okay? This down here, by the way, in case we get down to here, this is, of course, chlorine. Chlorine, okay? That is chlorine. That is a nitrogen and an oxygen, yes? ClNO, okay? So just keep that in mind, all right? I think that's all of them there. So we'll stop there for right now, and we'll see if we can get to some polyatomic ions here. We're going to go over some stuff here right away.